So class, continuing with the box Jenkins methodology. So examining correlation in a time series data. So as you know, the correlation basically is seeing how much a series varies with itself. Basically that is autocorrelation. So in the autocorrelation, as you can see, the autocorrelation formula in this case is, this is our original series subtracting mean, and this is the lagged version of the series. So when k is equal to 2, the lag basically is 2 here, and then we again divide by yt minus y bar the whole square. So this is autocorrelation. Why autocorrelation? Because you are having a series yt and you are seeing how it varies with its own lagged version, right? So now examining correlation in time series data. So recall that, so when you compute these correlation coefficients, it indicates how successive values of y relate to each other, right? So when you have a y1 and y2, which is the lagged version of this, we check depending on the value how much these two values are correlated. R2 indicates how y values of two periods apart relate to each other, right? So R2 means basically if I have y, so let's say we have y naught, the original time series, y1 and y2, right? And let's say y3. So this is time period 1 apart, time period 2 apart. So we can have this as R2. So how much memory, basically in this terms we call it as memory. So if we have a data, how much of this data is actually relating to this particular data? So it may have a high relation, it may have no relation, or it may have a very small relation. Anything is possible. So the autocorrelation at lag 1 comma 2 make up the autocorrelation function, or ACF. Again remember, ACF we consider all the intermediate values also, and in partial autocorrelation we ignore the intermediate lags. So autocorrelation is again a valuable tool for investigating property of a empirical time series. So we will see the autocorrelation graphs also. Then we have a white noise model. So in the white noise model, where observation of yt is made of two parts, a fixed value and an uncorrelated random error. So this is important here, uncorrelated, right? So we say that the given value of yt basically is a constant model plus some uncorrelated error. So if you remember the initial lectures on time series, where we had seen that a given yt, we had forecasted 8 different methods, right? Average, median, last 4, last 3, and all those things. If you remember that particular example, that is nothing but a white noise model. So we are given a constant plus some error value. For uncorrelated data, a time series which is white noise, we expect each autocorrelation to be 0. So when you have a white noise model, see, anything with an autocorrelation of 0, it means that, for example, if we have 2 points, let us use another ink. So once you have points P1 and P2, we should not take it as a point, let us take it as a data series. So let's say this is y and yt minus 1, right? So yt minus 1 is basically the lagged version of lagged version of yt. Okay, so here what happens in case of a white series model, when you compute the autocorrelation of these two series, the autocorrelation will be 0. That is nothing but a white noise model. So that means that given a series, the series has no relation to any of its future lagged data series, right? So that is nothing but a white noise model. Now consider the following white noise series. So there are 40 periods here from 1 to 20 and 21 to 40, and these are the values, right? So we have 40 values here. Now just see in the next example. So ACF, autocorrelation, right? So we have autocorrelation functions for the value with 5% significant limits. So if you know, what we do is, like, the standard formula people use is 1.96 divided by square root of n, right? So now since we have 40 points here, so this basically becomes, I'm talking about the 95% interval, 1.96 divided by root of 40, right? So just to simplify the calculation, you can just see that if I take the numerator as 2 and denominator is root 40, which will be close to roughly 6.5. So 2 by 6.5, right? It is very approximate, and which is equal to 0.3, right? Because 6 square is 36, 7 square is 49. I'm taking the midway. So you can see here, this value, basically the 95% interval basically says that the ACF, right, for the lags as you move along is all between the range. So basically, none of these are significant, right? All of them basically lie in this 5% bracket, right? So basically, these values are termed as statistically insignificant, right? So we do not consider these values. So that means that the data series in its successive lags has a very little relation as we move along. Now you may ask why we have taken only 10 lakhs. So for that also the statisticians recommend that it is 0.25 into number of values that you have. So in the previous case we had 40 values, so 0.25 into 40 basically has 10 lakhs. So not a golden rule, but just an approximate rule that it is always better to at least take 0.25 n. So if you, let's say, had 100 values, you would have taken the lakhs till 25, right? So again, this shows us for the white noise series that there is no significant relation between the current series and the lag versions of this. So the sampling distribution of autocorrelation, the autocorrelation coefficients of white noise have a sampling distribution that can be approximated by a normal distribution, right? So let me just focus on this point. With a mean of 0, right? So basically the autocorrelation coefficients, right? In the previous slide, these are the autocorrelation coefficient 1, 2, 3, whatever the value is. So this is roughly 0 minus 0.1. So all these values collected together, it can be approximated by a normal distribution with a mean of 0 and a standard error of 1 by root n, where n is the number of observations. As I told, in our case, n is 40. So this information can be used to develop test of hypothesis and confidence interval. So let us see the next slide. For example, in our white noise example, we expect 95% of the ACF to be within this. So if you see 1.96 by root n, basically plus minus, because above the x-axis and below the x-axis. So we have zero 0.3 plus minus. So let's say this is our normal x-axis. So this becomes plus 0.3 and this becomes minus 0.3. So we expect that 95% of the all samples should be in this particular range, right? So this is what this particular theory says. If this is not the case, then the series is it's not a white noise, right? So for example, in the previous case, if you see, we had nothing which was above the significance line. So in this case, it was 100% of the ACF values which were lying in this confidence interval, right? So definitely it's a white noise series. We will again see how when we have a different set of example where the data has trend, it may not correspond to a white noise series, right? Uh, so that's it for this lecture class. So in the next lecture, we cover more details. Thank you.